Hello, Jaguar students. It's your friendly neighborhood math teacher, Mr. Allred, and I would like to welcome you to Unit 3, mini lesson number 5 about similar figures. Today, we're going to take everything we've learned so far in this unit on ratios and proportions, and we're going to find some real-world examples of where we can use our knowledge, okay? And by the end of today's lesson, you should be able to explain how to use proportions to find missing side lengths in similar figures. If you're ready to work, that's awesome. Here we go. Today's mini lesson is your 8th entry in the table of contents on this lovely 6th day of November 2017. This is Unit 3, mini lesson number 5 on similar figures. Let's get ready to get to work by writing entry number 8 on the top right-hand side of our page and get ready to write down what I write down and try to learn something today about similar figures and their use in math today. Okay, similar figures are two shapes with proportional side lengths. That's a very, very middle school definition for you, but that's what they are. There are 3 ways that we can tell that two figures are similar. These following 3 things must be true. They must be the same shape, first of all, so rectangles and triangles can't be similar to each other. Okay, they must have the same angles within them. Their angles must have the same measurements. We'll be able to talk more about that later in the year during our angle unit. But the big important thing that tells us if they are similar is if their corresponding side lengths are proportional. Their corresponding sides are proportional. What are corresponding sides, Mr. Art? I don't quite understand. That's okay. We're going to look at what corresponding sides are here in this first example. So in this first example, it says, are these two figures similar? If they are, explain why. If not, explain why not. Corresponding sides, okay, are the same side on different shapes, the same side in the same place on different shapes. So BD right here on this triangle, yes, this triangle is bigger than the other one, but this BA side right here is taking up the same place that this ED side is. So they are both on the same part, the same side at the same place of 2 different triangles, okay? Just like that, AAC would be similar to DF, and BC would be similar to EF, okay? So they take up the same place on different sides. Corresponding sides are in the same place on different shapes, okay? So in the big triangle, I can write those 2 measurements as a ratio, 6/10, and I need to make sure that on my other ratio, I use the corresponding sides in the same place. So please note that 6 and 3 are corresponding sides, and 10 and 5, those are corresponding sides as well. So those are corresponding sides on different triangles, and that's why it's really, really helpful for us to look at it that way. Hope that makes sense so far. So I've written the big triangle, 2 of its lengths as a ratio, 6/10. And I'm going to write the little triangle of 2 of its lengths as a ratio, 3/5. But my corresponding sides line up. BA and ED are corresponding, and AC and DF are corresponding. Then, just like we talked about in mini lesson 3, if their cross products are equal, that means that they are proportional. So 6 times 5 is 30, and 10 times 3 is 30. That means their cross products are equal. So these are proportional relationships, which means that these triangles are similar. So yes, they are similar because they have corresponding sides being proportional. They have the same angles, and they are the same shape. So we can use this information about similar figures a lot to help us out in math in lots of different ways, okay? But before we talk about some of those cool things, we have to solve for some of these easy shapes first. Okay. Last week we solved proportions. If we had 3/9 equals x/27, tell Edpuzzle what you think that is. That's right. You should have cross multiplied and got 9x equals 3 times 7. That's 21. And you can divide both sides by 9. I mean, you divide 81 by 9. X should be 9 there for that one. That's awesome. Good job. So if you have 2 rectangles, so that was really helpful for us because it'll help us if we're trying to solve for similar figures. What happens if we know that rectangles A, B, C, D, and PQRS are similar? how could we find x? Okay, well, truth be told, this left rectangle, if you wrote it as a ratio, you'd have x over 8, where x, b, c is right here, and where a, b, 8 is right here. Okay. The tricky part about that is that these two rectangles are facing in opposite directions. So they're facing in opposite directions. They look different. They're faced differently. Okay. But BC is corresponding to QR. If I were to turn this rectangle to the side 90 degrees to make it oriented the same way as this one, QR would be in the same place as BC, and QP would be in the same place as AB. So those are the corresponding sides. So we said X was corresponding to 12. So I'm going to write X and 12 on the same level of my proportion. And we said 8 was corresponding to 6. So we write 8 and 6 on the same level of our proportion. Okay. I've shown the corresponding sides on the same level. Then I can take 6 multiplied by x, that's 6x, and 8 times 12 is 96. If I divide by 6, I get 16 there for that one. So that's pretty lovely. I get 16 there for that one. Sometimes the figures aren't turned the same direction, like they weren't there. Sometimes they're turned in opposite directions. Okay, same thing here for this first example, number 1. I have one rectangle that says 5, 8. One of the sides is 5 and one of them is 8 on that rectangle. Okay, if I were to orient the second one in that same way, then y would actually be corresponding to 8 and 3 would actually be corresponding to 5. So I'm going to have to write a ratio, a proportion that says 8 over 5 equals y over 3. I'm going to keep my corresponding sides lined up, and then I'm going to cross multiply. 5 times y is 5y, 8 times 3 is 24. When you divide both sides by 5, like we have been doing for a while, you get 4.8 for that one. 4.8. Okay. The last thing I'm going to show you for this second example is how to set it up, and then I'm going to ask you to solve it. Okay. And then I'm going to ask you to do number 1 on this next part on your own. Okay. On this next example, I've got 2 triangles. One of them has a base of 6 and a hypotenuse of Q. And the other has a hypotenuse of 5 and a base of 4. So when I was making sure I wrote this is a ratio, a proportion with corresponding sides, if I wrote Q over 6 for one ratio, I had to make sure I write 5 over 4 for the other. Okay, so I wrote the corresponding sides on the same level, just like I have been doing. If you solve for Q, tell a puzzle what you get. That's right. You should get 7.5 there for that one. Okay, now I want you to look at number 1 and see if you can set up a proportion and solve it and see what you get. Hopefully you got x equals 42. If you did not, we will keep working on that as we go through the day today. And I hope that you ask me some questions if you have any when you get to my station. Thanks so much for watching this notes video. I hope you make it a great day or not. The choice is yours. And remember that of all my students I've ever taught, you are one of them. Have a great day.